Okay, so my topic today is I'm talking about deterministic Ethernet solutions. So I want to reflect a little bit what are the advantages for space applications. When we look at the current network market, we will see that Ethernet is predominant. It's a worldwide standard. It's defined in the IEEE 802. So it's based on an open source, well-defined standard. There's a big community behind it. So the standard is updated and pushed with different additional quality of services all the time. It's based on an well-defined model. So here we see on the right side the OSI model, where we have the different layering concepts. It's not only the communication protocol itself, so it's also the stack itself. So it has a well-defined physical layer up to the different application usage. It's based, or it's currently, so the consumer market has driven it to be low cost, and it has a very, very robust physical layer. With future announcements, so currently we are talking about, for example, this broader reach physical layer, which is currently used in the automotive industry, which is 2-wire twisted pair up to 100 megabit currently. This becomes now less and less expensive, and it becomes less and less weight, and also the power is going down. To the physical layer itself, so the interface to the physical layer is also well established and defined in the IEEE 802 standard. And moreover, everybody learns about Ethernet in schools. But I want to reflect today what is a little bit the problem when using standard Ethernet solutions for, or let's say, event-driven communication solutions for reliable and robust applications. So we see here a switched Ethernet network with some network interface cards and some switches. And if we now want to here transmit data in an event-driven manner, so we don't know exactly who transmits at which time. And if we have a look now at the green packet, we will see that if the green packet went through the switch, and there are multiple other packets at the switch at the same time, then this green packet will here be delayed by an amount which is not really defined, so it's not really deterministic. When this went then over a second switch, we will see an additional increase of latency. This can be handled now by standard Ethernet features like prioritization or bandwidth limitation per port at the Ethernet switch itself, but we have no deterministic behavior at all. So what was the idea behind this time-triggered Ethernet technology we have established? So the idea was more that we have on the one hand side the static configured communication. So this means here we have performance guarantees, we have a real-time behavior which can be used for safety-critical applications. And there we have different standards and different protocols which have been available at this point in time, and we have the different applications which are going up to fail operational applications, so where we have to proceed in case of failures of the system. Here we have the high costs of the systems, and we tried to combine that with the IT multimedia infrastructure, where we call it free-form communications. So here we have no performance guarantees. What we mean here with real-time performance, for example. And we have here different open standards of communication. We have here multimedia applications, audio, video, and so on. On that side, we have very low-cost equipment. And the idea was how we can combine these two worlds in a new standard or in a new protocol standard. And the idea was here to have as basis standard Ethernet. So this means, according to the layering model, fully standard Ethernet compliant, and add in addition this airing 64.7 communication, or also known as rate-constrained communication, where we also have this asynchronous transmission scheme with defined latencies and jitters depending on the network load. And in addition to that, we have added a quality of service which is full synchronous. So we have here a full synchronous behavior, and therefore we need some kind of synchronization in the network. And on top of this synchronization, we then transmit messages according to a predefined schedule. Here we get down to very, very low jitters and well-defined latencies depending on the setup itself. And this is then a quality of service for standard Ethernet that enhances standard Ethernet to be able to be used for high reliable systems. As I mentioned, what do we need to establish this time-triggered services? We need a clock synchronization in the network. And how does this work? So here we can define different of these time masters, and these time masters, they provide their time information in these frames into the network. And the network itself, so the switches, they are calculating an average out of the different time information they get from these time masters. So per configuration, you can define who are these time masters in my network, and they will then transmit their messages or their time information into the network. The switches will calculate an average, and then they will distribute that to the whole network. And the network can synchronize to this clock synchronization mechanism. What can now happen here? So we can now have here different faults, and these faults can be tolerated accordingly. So it's not like in 1553, where you have one time master providing the time information for one bus line. So here we have really a distributed network, and this network has multiple time sources and creates a global time according to these time sources, and can here now tolerate multiple faults in the system. A short example, you would think of how can this be established, and then you will get to some problems for this establishment. So if here we have a very simple network, we have here a sender A and a sender B. So these are these time masters, and these time masters now sending out these time frames. And now it can happen in this very simple example that the sender A transmits a message at 10, and the sender B transmits a message at 10:05. However, during or because of the different latencies of the lines, it can happen that the message from sender A is received here at 10:20, and the message from sender B is received here at 10:10. So what happened is that because of the setup, of the architecture, of the topology, whatever, these two messages have changed their order. And this makes a big problem in a lot of different applications. And here it makes a problem for the synchronization establishment. So how can we deal with this concept or with this problem? We have to find a way to delay these frames in the receiver to get back the sending order. And how are we doing that? So we are using a term called permanence delay. So we delay the frame. And how long do we delay it? We delay it by a maximum transmission delay. So according to the network setup, I know a maximum delay from the sender to the receiver. And I take this maximum delay as, let's say, static parameter for my network. And then I subtract the transparent clock delay. What does that mean? The transparent clock delay is a delay value that each component adds into that frame. So this means the frame itself has some kind of payload, and this payload tells me how long did the frame travel from B to C. So it accumulates the dynamic delays or the delays of the network. And when we use these two terms now, we can here find the permanence point in time. So this means when will the frame become permanent at the receiver. So we calculate The permanence point in time is the receive point in time, so when the receiver receives the frame, plus this permanence delay. So we delay it virtually in the receiver. And what happens now, if we go back to this example, we can see here that the frame from B arrives at 10:10, so the receive point in time is 10:10, plus this 30, so 30 is here our maximum transmission delay, minus this 5 is the 5 minutes how long the frame traveled from 10:05 to 10:10. And then we will get back here 10:35. If we do the same for the frame from sender A, then we will see here that the permanence point in time for the frame F1 will be 10:30. And we will see that we will get the sending order back. So this means the frame here now arrives at 10:30 from A, and the frame from B arrives at 10:35. So we have back the 5 minutes of the sending order, of the sending timing, so that we have the right sending order. And we are doing that for the clock synchronization. So we established at one time, and then all traffic transmissions according to the synchronization have the correct order. So in the network, a frame will never arrive before another frame if the sending order is accordingly. If we have established this synchronization, it's then possible to synchronize it two different absolute clocks. So here we are talking about a relative synchronization, and it's possible to now synchronize this relative synchronization to an absolute time. This means you have here, for example, GPS, you have an absolute time base, and then every communication participant in the network would see the GPS time. It is also possible to have your gateways, for example, to space fiber. These gateways can be, for example, in the switch here, or it can be in an end system. And here you have, for example, standard Ethernet or this AFDX traffic. It can all integrate into the same network. These are just different traffic classes, but are all based on IEEE 802.3. So if we now have established this synchronization, this should be shown here by this clock. So we have here a network, we have here a sender, then we have switches, so a switched network again, and then we have here a receiver. And here we have also, this should show a standard Ethernet end system, for example, a standard PC. If we transmit the message here now, so all these components, they keep a configuration and they work according to this configuration. And if we transmit the message M here at 10:45, then the message will go to the switch and will arrive at the switch at a dedicated port within a dedicated acceptance window. So this means at the switch port here, we exactly know that the message will arrive within that time window. If the end system would now be faulty and would transmit, for example, as babbling idiot, frames to the switch would only accept these frames within the time window and acts therefore as active bus guardian in the full network. The switch itself is doing store and forward, so he receives the complete frame, checks the frame accordingly, so this means CRC, frame layout, and so on, and then transmits the frame at a defined point in time to the next switch, which has, again, an acceptance window, and then forwards the switch. This can now be at the same point in time, or it can be at different points in time. What is happening now here? Here we see exactly, or we exactly know when we will receive this frame M accordingly. Here, for example, the precision of this window is depending on the synchronization precision. So this means I can establish a higher granular clock on which the scheduling is based, and this higher granular clock depends on the precision within my network. So typical precisions here are in the area of 100 nanoseconds, for example, depending on your setup. If we have here a standard Ethernet component like a laptop or a standard PC that can be connected to the same network, it will receive the message, but it has no real time information. So it does not really know when the frame will arrive and what's the global time in the network, because it's standard Ethernet. So it's a standard Ethernet frame. What we see here is that we now get a defined latency from the sender to the receiver. So this means we exactly know when the frame is sent, we exactly know when it is received, and we exactly know the jitter within the network. How is that implemented? So when we look to the OSI model, then we see these services for this clock synchronization, for example, so startup, recovery, and this fault-tolerant distributed clock algorithm. They are implemented on layer 2, and they are just additional quality of service to the standard Ethernet layering. So this means there is no modification on the frames or something like that. Also on top, you can run the standard Ethernet stack, so like IP, UDP, TCP, depending on your needs. And also this rate constraint traffic is also just an additional quality of service to standard Ethernet. When we look to it on another perspective, so this should show an Ethernet cable. So here we have a full duplex Ethernet cable, and this can be virtually partitioned into this time trigger traffic, into the synchronous traffic, into this rate constraint traffic, and into the standard Ethernet traffic. But what does that mean on the line itself? It means that there will be periodic traffic. This would be the time trigger traffic, for example. And this is scheduled according to the synchronous time. And then in between, there can be this rate constraint and this standard Ethernet. So this is event-driven traffic, and this will consume the gaps between these time-triggered frames. So depending on the configuration, the time-triggered traffic can be higher or lower, and then it opens a window for rate constraint and standard Ethernet traffic. What we see here is that this traffic, so the time-triggered traffic, always becomes periodic, whereas the rate constraint or standard Ethernet traffic, so event-triggered traffic, is here fully event-driven. I want to show you here a slide, for example, which have been done in the NASA Orion context. So it's a slide from NASA or from Honeywell. Here there are different mission scenarios where this synchronization would really make a lot of sense for control. So for example, if you look here, we have this Orion vehicle that's docking to a lander, and then we have two networks, and these two networks are integrated during the docking maneuver, and we have here now, we want to have here now time trigger traffic, because the vehicle here, so the capsule, for example, wants to control the lander vehicle. So this means we have control loops during the landing, and therefore there are different priorities implemented in the protocol. So this means here we have a network with a higher priority, and here a network with a lower priority, and when the two talk to each other, the one with the lower priority would take over the synchronization from the one with the higher priority, and is then able to communicate full with this, let's say, defined latency and this minimum jitter, and would be able to control this lander vehicle. And the idea here is, for example, there is different mission scenario where something goes up, then it docks to each other, does some mission, and then goes back. However, this is a little bit about the protocol and the capabilities of the protocol, but I want to show you here what are the capabilities of the protocol for the software development. And we are seeing here, so this is a research result from the University of Illinois. They have done a comparison between synchronous and asynchronous communication within a system. And they have seen that in this very simple system that they found, if they drive it in a synchronous way, they found 185 reachable states of this system. And then they did the same for an asynchronous model with no latency in the communication. And they found out that these are 3 multiplied by 10 times 6 states in the system. And then they tried to do the same for an asynchronous model, so for the same as here, but with varying communication latencies. And then they found out that these states are 10 times 8 to 10 times 10. around 10 times 8 to 10 times 10, and they were not able to calculate it with at this time they had a PC with 8 megabyte of RAM, and they ran out of RAM. So what is the idea now? So we all know there is currently a lot of push for this IMA, so for this time and space partitioning, and the idea and what is currently followed within the civil aviation industry, as well as, for example, in the automotive industry, is that you have this time and space partitioned module or operating system where you have your modules, and these modules are loosely coupled. So they have a synchronization between, or the partitions are running according to a dedicated schedule. They get some hardware resources, but the communication between these two models is not depending on the time. So they are loosely coupled. And what can you do now by using, for example, these synchronization mechanisms is that you could combine these different models into a distributed embedded computing system. So you use the synchronization of the network and the partitioning of the network. You connect these two modules, and then you get to a system where you can easily do distributed computing, redundancy management, and so on. This brings us then to the software architecture itself. So running these software applications on an asynchronous communication always brings a lot of difficulties when it goes for voting, when it goes for example, for sensor fusion, when it goes for control loops, and so on. When we run that on a synchronous communication media, we could reduce the complexity because we exactly know the interfaces and the temporal behavior of the interfaces, which could then lead to, depending on the architecture, depending on the development, could lead to a reduction of the software application code itself, as well as this middleware functionality. How can this look like? By using this time-shifted Ethernet technology. So here, for example, you can see that this TT Ethernet N system here, so this controller here, uses dedicated memory. So this means not only the network is partitioned, also the memory here is partitioned. So there are different partitions, and these partitions are fully independent from each other. So this means you could associate, for example, a partition here over a time and space partitioned operating system to an application. And these applications then really work fully independent on the dedicated partition and have no influence to each other. So if one partition here would crash, then you have the full functionality of the network available without this one partition. Just to show you what's currently available, so this is some kind of product. So we have development products, ruggedized hardware, development systems, and so on. Just to give you a short overview, what are we doing in space here? We are going for, so we are currently implementing, so we call it Space Pegasus. So we have a cross-industry development. So you see here with full DO and ECSS qualified products. This means we develop cross-industry, we develop for civil aerospace, for example, and there we have the full DO certification leverage here also for space. And then we are going into the dedicated IPs, which are available, and then it goes into a chip, and this chip will then be available in a plastic housing and in a ceramic housing. So there would be on the one hand side a low-cost chip and a full space quality chip, and these two can then be used depending on the usage. Also, there will be dedicated space products where we have currently different customers here. Just to give you an overview, when is that available? So the IPs are currently available, and the ASIC itself will be available by mid to end of 2015. Also the products, I think I'll jump over that. I have some more slides. Another topic which has been discussed during the day and also yesterday is the complexity. So how can we handle the complexity? And one thing is we call it composability. So this means there are different modules or different subsystems and this can be now provided by different suppliers. It can be provided by the same supplier. However, these modules have some kind of complexity. So each of the module has dedicated states, and during the development, everybody tries to test his module accordingly. But what happens then during the integration phase? So we would assume that the complexity is that, but then it often turns out that the complexity is much higher because of the use of a not defined interface. So this means if we have an interface that is, for example, event-driven, it can easily turn out that the complexity of the system is much higher, and then it leads to cost overrun and so on. How can we restrict that? So going from event-driven communication to a TDMA style partitioning or communication concept with well-defined interface, and then this would bring a lot over the whole life cycle. So starting from software design, testing, certification. So here we are talking also about upgrades, reuse, recertification, and so on. Just very quick, I show you a concept of Orion. So this is, for example, the Orion vehicle, and they are talking here about a virtual backplane. So this means the physical architecture may look like that, but the architecture which the different components see or which the software sees is here. For example, we have different units, and these different units are placed on a virtual backplane. They get dedicated resources, and they see over this virtual backplane the information of the whole communication between the different units, but they do not have to take care about any interfaces or something like that. The application software is running in these units and gets the dedicated resources. There is another project we are working on, so it's a project from the DLR, and there is the idea to have different levels of quality and performance, and that there can be simulation systems running on the same network and easily be plug and play on the same network as, for example, the flight hardware. So this is on the one hand side the simulation, or let's say a very cost-efficient test equipment, and this runs on the same network as the onboard avionics, and the whole architecture is network-centric. I show you another sample that we are a little bit more across industry. Here, this is the autonomous drive platform for the new Audi A8. In the core of this, there is a time-triggered Ethernet switch. And why are they using that? Because they want to reduce the memory usage of this board. If there is no, let's say, time-triggered communication, if it would be event-driven, here we have around 13 gigabit of data running through the board, and this would cause a lot of buffering of the different video and radar data at the board. Just an overview what the standards are about. So TT Ethernet is based on this SAE AS6802 standard that has been established by Honeywell, NASA, Lockheed Martin, and so on. So there was a strong community behind it. Then there is currently an initiative with Cisco. So Cisco is going, or let's say together with Cisco, we are going for an 802.1 time-sensitive networking standard. So this means it goes more into industrial and into the IT market. Here it goes more for, it's not as high reliable and available. It's no fault tolerance included here. It goes more to an additional quality of service by meaning of latency and determinism. And then there is a big initiative from automotive currently for Ethernet, which is here driven by Audi and VW. And here there will be another standard for Ethernet within automotive. And currently we are working on a CCSDS standard for time-triggered Ethernet because the aerospace standard defines the protocol principle, but this would be more into the direction how to implement the technology itself into the dedicated components. Thank you very much. Are there any questions?
So I've never really looked at Ethernet in a space-based application, but what's the swap like compared to SpaceWire?
So for example, it always depends. So there is, for example, the synchronization mechanism has for sure some kind of complexity, but the benefits you get, what you have also seen in the reduction of the application, the middleware layer, is, in our opinion, much higher than what you have, for example, or let's say what you need in addition in complexity in the hardware itself. And we have compared, for example, the IP blocks to SpaceWire, and there is no real, so it's not really bigger. It always depends on what you want to do. Yeah. So, for example, with Ethernet, you have for sure a lot of features that you could use or you do not use. Yeah. So when I tell you that Cisco, for example, they are working on the biggest ASIC which has currently been produced, because they integrate all the security features of standard Ethernet as well as all the other services, and then it gets big. But what we are targeting here is high reliable applications. So the same technology is flying, for example, in a demonstrator for a Sikorsky helicopter. So it's really fail operational, and therefore we have to reduce the IEEE features to a minimum subset, which is able to be handled, yeah, because otherwise the certification would not be possible of the technology. So there is no big difference when you compare it. Yeah.
Okay. And are you also thinking of building in any type of dual redundancy, which is a big seller on something like 1553?
Exactly. So there is built-in redundancy for up to a dual fault tolerance, but this is also a matter: do you need it or do you not need it? Yeah? Depending on the application, you can decide if you need it or if you don't need it. Yeah?
Any other questions? All right, thank you.
Thank you.